Good morning. Um, okay, let's get started. Everybody, can you see my screen?
Yes, sir, we can see it.
Yeah, like DC generator and motor principle. Um, so far, we have covered the most of the AC machines like synchronous motor, synchronous generator, induction motor generator, transformer, three-phase system. Uh, Today and the next class, we will be looking the DC machines. So one of is DC generator and then DC motor. So they have also some applications in real world practice, although in a small scale, not large scale, but still they have a lot of applications. That's why we will be looking their working principle and then followed by some numerical problems.
Dr. Ali, could you tell me what chapter today is from?
So from the book, this is chapter, just a moment. Uh, Hold on. This is chapter 8.
Okay, thank you.
Yeah, from the book we are following, that is chapter 8. Okay, now let take you to that whiteboard for a moment and then you will get it. Okay, so I mean similar to the AC generator, especially the synchronous generator, a DC generator has also the armature and it needs the magnetic field. And that is the common principle to build a voltage in any generator. So for example, this is the armature. An armature has coil, this coil. So you see that because this is not AC generator, this is not three-phase system. So we will just show only one set of coil because this will be the DC generator. So I assume that, okay, this is the set of coil that is placed on that armature body. Let me write down armature body, this body, and then there is magnetic poles. Of course, you need magnetic poles. For example, this is north pole, and then this is south pole, just on magnetic pole, and then of course it has the shaft. This is the shaft for the armature, and then that shaft is moving at a certain speed with the help of the prime mover. Now, we are discussing that DC generator. So in case of DC generator, armature rotates, but the field remains static. You see, this is just opposite to the synchronous generator. In case of synchronous generator, we learned that magnetic field rotates with the help of the shaft, and armature remains static because armature has three-phase coils and during the movement those coils might be deformed, they might be shorted. But in case of DC generator, you know, hardly here 1000 volt is produced, that is the maximum. Typically 500 volt, 400 volt, even the much lower voltage in case of DC generator. That's why in case of DC generator, common practice is to rotate these coils. In other words, rotate the armature with the help of the SAM and keep the magnetic field static. This is just the opposite to the synchronous generator. Keep in mind. Okay. So, and then once with the help of the prime mover, this shaft rotates, then the voltage will build up here. So, and then that is that DC voltage. But now, actually, what happens initially, it is not the DC voltage. It is not DC. Initially, AC voltage is produced. The reason is that you see the coils are moving with this arrangement, but the magnetic field is fixed. But this is north pole, this is south pole. So therefore, you see These coils, once coming under the area of South Pole, and because they are moving, again they are going under the area of North Pole. So consequently, the effect is opposite to the North Pole and South Pole. Therefore, at the beginning, in fact, the AC voltage is produced. For example, this is under the area of North Pole and this is under the area of South Pole. In that way, it is going on at the beginning. But then because we are talking about DC generator, that's why there is a commutator segment. It is called the commutator segment. After producing AC, there is a component or parts which is called commutator. Commutator is very similar to rectifier. Commutator is kind of the rectifier. So you all know the function of rectifier is to convert DC AC into DC. Similarly, in case of DC generator, there is a component or parts attached with the coils, which is called the commutator. This means this body is the commutator. That body converts into the DC. So this means actually in real practice, even though it is called DC generator, initially AC voltage is produced. Now you can say, irrespective of the type of the generator, whether it is DC or synchronous generator or induction generator, at the beginning AC voltage is produced because of the change of the magnetic poles. So this is the nature. But we want to utilize DC. That's why a similar device, similar to the rectifier device or component, which is called commutator, that is used, and that converts into DC. So that is the basic principle of that DC generator. Now, there are several things. So in case of DC generator, the initially the voltage that is built up, so it has several factors. So you will express E equal to that phi is that flux. It is called G, number of conductors I am coming, and then N is the rotational speed. It is typically designated by the symbol N, then 60, then multiplied by phi over A. So in this case, your phi is that flux that is coming from here. So phi is your flux. This is flux. G is the number of conductors. So which is your G? So this means that, so how many conductors are here? Now, for example, this is called one turn, but one turn has two conductors. From here to here, this is one conductor. From this point to this point, another conductor. And then when I am twisting, another conductor. And when I am completing the turn, another conductor. Then fifth conductor. In that way, you see, therefore, this is called one turn of the coil, and one turn has two conductors. That is the definition of this J in the equation. Therefore, in the in this arrangement or in this coil set, how many conductors, that is represented by the capital letter Z, and N is the speed of the shaft in RPM. This is in RPM, revolution per minute. Okay, and then P is the number of pole. How many poles? It is 2 pole or 4 poles. In most cases, it is just 2 pole. So this is the pole number. This is the number of poles. And then A is called parallel path. Let me write down. A is called number of parallel path. Now here in real practice, in real world generator, I mean, I have just shown one set of coil just to explain you the working principle. But in real practice, here in fact, there can be another set of coil which are placed in parallel. For example, in case this does not work, then this will work. or even there might be another set of coil. So therefore, these are called the parallel path. So A is the number of parallel path. How many parallel paths are in the coil? So therefore, when you will be solving the any numerical problems, this will be given. Okay, parallel path 2 or parallel path 3 or parallel path 4. So in that way it will be mentioned. Pole number will be mentioned. Every component so will be mentioned, and then you need to calculate the induced voltage A. So I think they already, because you all have understood the synchronous generator, and that is three phase. So it is not difficult to understand the working principle of DC generator. So everybody, do you get it?
Yeah, I sure do.
Yeah. So therefore, I have written down this equation in another slide. So you are getting in plain version. So let me take you there. Okay. Okay. So everybody see, I have written down that equation that was there. Generated voltage in a DC generator is phi Gn over 60 multiplied by phi pi. And then I have written down the meanings of those symbols. Like E is the generated voltage, phi is the flux per pole, G is the total number of conductors, N is the rotational speed in RPM, and P is the number of poles, and A is the number of parallel paths. Uh, I would recommend each of you, can you please note down this equation? I mean, soon today we will solve some numerical problems. I mean, uh, with your pen and paper, you will be doing with me some numerical problems. So please, everybody, write down this equation and then write down the meaning of those symbols. Phi Gn by 60 multiplied by phi by A. A is the number of parallel paths, P is the fold, N is the speed, phi is the flux per pole, and G is the total number of conductors. Have you all written down this equation?
Yes, I have.
Yeah, so just the very first equation. You don't need to write second or last equation. I am coming that point again, because this equation and this equation related to motor. I mean, today I will be discussing that thing. Uh, the motor generator is pretty much the same thing, just it depends on the mode of operation. Okay, so and have you written down the meaning of those symbols? Have you all written down? Please write down the meaning of those symbols in the equation. Like E is the generated voltage in volt, phi is the flux per pole, capital G is the total number of conductors, and capital N is the rotational speed in RPM, phi is the number of poles, and A is the number of parallel paths. Everybody, are you writing? Or are you done?
Yes, I got it.
I've got it too.
Okay, okay,
Yeah, I've got the first half.
okay, okay. The first equation and the meaning of those symbols. Yeah. Okay, so therefore now I'm taking you to a numerical problem. We will be utilizing this one. Um, Everybody see, there is a numerical problem. I have written down the answer for you so that you can right now verify using your pen, paper, and calculator. Read the problem. The shaft of a 1.5 horsepower, 4-pole, 60 hertz, single-phase synchronous motor is coupled to a 2-pole DC generator. Now, I mean, you might be surprised that, okay, why I'm talking about synchronous motor single phase. Basically, that is working as the prime mover for the DC generator. So you see, that's why that single phase motor, synchronous motor, is coupled to a 2-pole DC generator, meaning that they are sharing the common shaft. Both the synchronous motor and DC generator has the same shaft. This means that synchronous motor is working as the prime mover, because you need some sort of rotating means that will rotate the shaft. In this case, synchronous motor is serving that purpose. This is the prime mover. Like, we are not using any oil-based or gas-based or nuclear-based, not any turbine. Synchronous motor is working as the prime mover. That is the meaning of the first sentence. So therefore, all those ratings are related to the synchronous motor, horsepower, 4-pole, 60 hertz, but DC generator has 2-pole. Okay, then moving forward, if the total number of conductors in the armature winding of the generator is 100, the flux per pole is 0.05 Webers, then calculate the generated voltage and required torque of the motor in order to produce that voltage. Then assume the number of parallel paths is the same as the pole number for the DC generator. Now, as you can see, this is clearly the DC generator voltage calculation problem. The synchronous motor is just working as the prime mover. So that's why the question is coming. Calculate the generated voltage and required torque of the motor in order to produce that voltage. So first you will be calculating the voltage, and I hope you will be getting result 150 volt, the answer. And then once you do that, the next question, what is the amount of torque to produce that voltage? This means that in this case, torque is coming from the shaft. Who is driving the shaft? What is the main driving force? That is the single phase motor. So you have to calculate what is the amount of torque provided by the motor, in fact, in order to produce this amount of voltage. So two questions. So therefore, everybody see, for the first part, I have drawn a picture. Everybody see this picture? This will be the picture. This is your DC generator. I'm just showing brief schematic. It has the coil, it has the 2-pole, and it is producing that voltage. Now you see, you need the prime mover. This is the shaft of the generator, but this is the common shaft for the synchronous motor and generator. That's why in this case, first you are starting the synchronous motor, and that started spinning. Consequently, because it is the same shaft, DC generator shaft is also rotating. That is the meaning. So this will be your schematic. And then I have written down the rating for the motor, 1.5 horsepower, 4-pole, 60 hertz. But you have to find out the voltage here. So now everybody see, because the first question is calculate the generated voltage. So that's why first everybody see, I have written down that equation, E equal to phi gn over 60 multiplied by phi by A. And you see, from the statement, I have plugged in all the numbers. Therefore, everybody, you have that equation that you have already written down. Now you see how you can fill that thing. So now everybody see, capital J, total number of conductors is 100. That is given. Flux per pole, that is also given, 0.05. Okay, and then pole number is given, which is 2. This is 2. You see, don't mix up. 4-pole is for the synchronous motor, but 2-pole is for the DC generator. So in the equation, you have to use 2. Okay, and then see the very last sentence, assume the number of the parallel paths is the same as the pole number of the generator. This means that because the DC generator pole number is 2, parallel path, which is that symbol A, this is also 2. Therefore, see, 2 by 2, 2 by 2. Now, you need n, speed of rotation, right? In the equation, capital N stands for speed of the generator in RPM. But that speed is coming from the motor. So you see, in case of synchronous motor, what is the speed equation? Everybody say everything. And 120 F over P. That is the synchronous speed equation. And then frequency 60. Motor pole number is given, which is 4. You see, I have written down from that statement, very first line. 4 pole 60 hertz synchronous motor. This means that is the speed. So therefore, we are getting 1800 RPM. So this 1800 I have plugged in the E equation. And then finally I'm getting on 50 volt. Everybody, are you calculating? Are you getting me?
For the parallel path, you use 2.
Yeah. So because you see the very last sentence, see, assume the number of parallel paths is the same as the pole number for the DC generator. So
Got it. Thank you.
yeah. So in the second line, you see the pole number is 2. So this means parallel path is 2. So that's why I have like put here 2 over 2. This means P2, A2. And then I just showed how to calculate the N on the left side. And keep in mind that is coming from the synchronous motor. Directly, the speed of DC generator is not mentioned, but because it is the common shaft, so it will be the same. Everybody, are you calculating the E? Everybody, please take your pen.
Yeah, I'm working on it.
Okay. So Nathan, so did you get on 50?
I'm actually doing the math right now, but I think that's probably what it's going to be. 1 second. I'm writing down everything, so it takes me a second to get.
Oh,
Get there.
okay. Nathan, have you seen this problem? Because I am going back and forth slide. So
Yeah, I was able to write it all down. I got it.
oh, okay, very good. So therefore, you see, the I calculated and I got 150. Sam, did you get 150?
Yeah, I got 150. Sorry.
Okay. Oh, okay, great. This is not, that difficult. I mean, once you place, but the thing is that from the statement, you have to understand that, okay, how it is working. Therefore, you would not be surprised to look that at first synchronous motor is mentioned. This is not the synchronous motor problem. Mainly, it is just the driving force behind the DC generator that is working as the prime mover. That's all. But the rest of the thing is for the DC generator. But there is second part in the problem, you see here. Calculate the required torque of the motor in order to produce that voltage. This means you got the answer that DC generator produce on 50 volt. To produce that voltage, what was the amount of torque needed? That's the question. So therefore, who is providing the torque? Synchronous motor is providing the torque. So that you have to calculate. So therefore, if you see the very first line of the problem, the shaft of a 150 horsepower, 4 pole, 60 hertz. So this information is enough to calculate the amount of torque of the motor. So this means, you see, I have written down here torque of the motor. So before we have used this equation, power over speed in radian per second. Then the torque unit will be Newton meter. So this power is for the synchronous motor. So this is synchronous motor. Therefore, power is 1.5 horsepower. 1.5. So that's why, because P is in watt, I am converting into watt by multiplying that HP value by 746. And in the denominator, it will be speed in radian per second, which is omega. But here you see I am showing the omega. Again, that omega is for that motor or for the generator. So we have already calculated speed in RPM. Now we are converting that RPM into radian per second. You see here I have written omega, this 1800 multiplied by 2 by over 60 radian per second. Like I approximated 188.5 radian per second. That thing will go in the denominator. And then finally I am getting approximately 5.94 Newton meter. This is for the second part of the problem. Everybody, are you getting me?
Yes, you converted the horsepower right there for the 1.5.
Yes, right. So you see in the statement at the very first line, shaft of a 1.5 horsepower, 4-pole, 60 hertz single phase synchronous motor. This means these all three parameters are for the motor. So therefore 1.5, this is horsepower, you have to convert into watt. And then by using 4-pole and 60 hertz, you have to calculate the speed in RPM, and then you have to convert into radian per second. That I am doing here. So you're right. So phi was 1.5, I am converting into a watt by multiplying 746. And then look in the denominator omega, this is 188.5 radian per second. So you should be getting 5.94 Newton meter, that value of torque. Everybody, please use your calculator, then it will be a good practice for you. Nathan, did you get this torque value?
I sure did.
Okay, great. Hello, Sam, did you get also the same number?
I'm not quite there yet, but I did get the 150.
Oh, okay. I think Sam, some noise is coming from your speaker.
Sorry,
No, just
Jared
wait.
and I are in the same room, so it happens sometimes. But I got the 150, but I'm still catching up on the torque.
Oh, okay. So you see, like I'm showing the solution. So in the torque equation, it is P over omega, but then P value should be in watt. You have to express. But horsepower is given. That's why you need to convert into watt by multiplying it by 746. And then omega is not RPM, omega is in radian per second in this basic equation. Everybody please do use your calculator, then like it will be practice and you would be ready again for the other homework and the midterm exam, final exam, etc.
Dr. Ali, are you there?
Yeah, yes.
Okay. I'm good if you want to move on.
Oh, you got the same result? Hello, Sam. Did you get 5.94 Newton meter?
Yes, sir. I'm good.
Okay. Okay. The voltage value is also the same, right? Yeah.
Yes.
Okay. Okay. So therefore, as you see, I have already posted this on, I mean, in the last night, and then again at home you can see. So here everything is clearly mentioned. So please you make practice. So that is what I am asking. Okay, and then moving forward, I have one more problem, and then I will start discussing about DC motor. Everybody see, I'm going to the. Please read this problem. A two-pole DC generator having a safety speed of 750 rpm, 80 conductors in the armature windings produces 2000 volt. If 10 ampere current flows through the field coil with 10 turns, then calculate the inductance value of the field coil. Assume the number of the parallel paths is the same as the pole number. So in this case, what I am asking, what should be the inductance value of the field coil? So you see that what is the function of the field? Field is giving you the flux. Field is providing you the flux. Without the flux, you can't generate voltage, even though you have the shaft system. Shaft might rotate, coil might rotate, but if there is no magnetic field, then there will be no flux and no voltage production. So that's why for this DC generator system, what I am saying at the middle of the third line, if 10 ampere current flows through the field coil, this means field coil current is 10 ampere and field coil has 10 turns. This turn is related to field coil, not the armature coil. Then what should be the inductance value of that field coil? This means L value. And then also number of parallel paths is same as the pole number. So you see, read the first sentence once again. For DC generator, pole number is given. The safety speed is given. Total conductor G is given. And then even the voltage produced itself is given. The 2000 volt. So therefore, what is missing? The missing point is the flux. So therefore, if you use that equation, then you will be getting the flux. So everybody see? I have written down that equation equal to phi Gn over 60 multiplied by phi by A. And then I am plugging all those given values. Voltage 2000, G80, 750, 2 over 2. And then only phi, this value is missing. So from here, I got 2 wavers. So therefore, this is the flux 2 wavers. And then question was, what was the inductance for the field coil? So this is the equation, L equal to N phi over I. So from here, L is number of turns is 10. We got phi 2 from here, and then current flows is 10. So 10, 10 cancel. 2 Henry is the answer. Everybody, again, you take your calculator and then see that this is correct. Everybody, do you get me? Do you understand this one?
Yes, I understand.
Yeah, great. So therefore, once again, like for a moment, this was the problem. I have written down the answer here, 2 Henry. So DC generator, several specifications or ratings are given, even the voltage is given. So therefore, definitely, because voltage value is given, by using that equation, you will be getting phi. amount of flux. And then this is the question. If 10 ampere current flows through the field coil with 10 turns, then calculate the inductance value of the field coil. And then again, number of parallel paths is the same as the pole number that is mentioned. So that's why first I'm writing down that equation and plug in given voltage and other parameters. From there, I am getting phi. But this phi is of the field coil. This phi is from the field coil. That's why for the field coil, I am writing the equation, because field coil also a coil, and coil means inductance. So that's why L is N phi over I. And then I am just plugging those numbers. Number of turns 10, this phi 2, and then current value is 10. So I am getting 200. Everybody understands this one?
Yes. There.
Yes.
Writing.
Okay, great. So therefore, again, because this is given, here, so I mean already posted, so you can see these things again later. So now moving further, there are other problems that we'll be doing with me. Moving further, so let's have a look this one. We understand that generator, but the same device we can use as a motor. So that's why I have written here. So I'm taking you to board to understand generated or back voltage in a DC motor. This one. This back voltage is important, which is that. So I'm coming that point. And then I have written one thing which is called starter. And just for a moment you read it, and I am explaining going to the board, then you will be clear. To protect the armature from initial high current, a starter, which is called series resistance, is used in the DC motor. And once the back EMF is developed, the starter resistance is sorted out. So what does that mean? So let's take you to the board. Let me clean up some of the things. Okay, so let me show the south pole. So you see the picture is the same because it is motor generator, just the mode of operation. Now we are discussing the DC motor. So in case of the DC motor, clearly you understand that initially the shaft is not rotating. We have to make it rotate. So that's why I'm not showing the direction yet. So because this is DC motor, so what we have to do, we have to apply the voltage. So for example, we applied terminal voltage VT. So now you see this is the direction of the current flow, for example, IA. And then these coils, although mainly they are inductance, but they have some small resistance. So therefore I am just showing, okay, this is the small resistance. Let me draw in a bit here. Okay. Let me draw that resistance here. So for example, this is that RA, armature resistance, and this is the direction of the current flow. Okay. So you see, everybody see, we are discussing DC motor. First, we applied some DC voltage, which is VT, and then current is going to the armature coils. And now we are assuming this magnetic field, North Pole, South Pole are magnetized. So this means they are emitting, they are injecting the flux in the system. Now, what happens when you apply the voltage VT on the coils? Then according to the flux principle, flux will be produced. Definitely flux will be produced. This is phi A, armature flux. And then there is another set of flux that is coming from the North Pole to South Pole, and then this is going. So this is another flux, which is phi M. the main flux, and phi is coming from the armature. Now, we discussed in chapter 6, induction motor principle, that to produce torque, you need two sets of flux. I mean, at that time, you notice there was a stator flux, rotor flux. In this case, this armature flux and then this main field flux, if there are two sets of flux, then they can interact and they will produce torque, and hence the motor will start rotating at a certain speed. For example, that speed is n. So therefore, this is the sequence. First, you applied the voltage on the armature coils because current is flowing. So consequently, there is one set flux, which is phi A, armature flux. And already you have magnetic field that is causing another flux, which I have defined phi M, main flux. Now, as a result of interaction between these two sets of flux, torque will be produced on the system, and hence that shaft will start rotating. Now, everybody say, once that shaft has started rotating, so what will happen? Because the shaft is rotating, meaning that these coils, armature coils are moving. Yes, armature coils are moving, but this field is static in an south pole, north pole and south pole are fixed. So this means that because now there is relative motion between these coils and this magnetic field, there will be voltage built up on these coils, which is called the back voltage, which I will define by the symbol E. This is the back voltage, EB. So everybody understand which one is the EB? After starting rotating the shaft, on voltage build up on the armature coils, on the main coils. That voltage is EB back voltage. Why it is called back voltage? Because it will start opposing the main terminal voltage according to Lenz's law. Again, this is called, the Lenz's law. So according to Lenz's law, the voltage produced because of the initial applied voltage will start opposing it. So it is called the Lenz's law. So this means that if I write down the current equation, armature current, how much current was entering into the coils. So actually I have to write down this equation, that terminal voltage I applied. This is the initial applied voltage to the motor, and later back voltage is built up, EB, and then divide by this resistance, RA. And you see, this makes sense. In other words, if I write down here, like VT, this is my main voltage, applied voltage. This voltage, I am calling it back voltage, we generated, you see, plus IA into RA. This will be the voltage. Everybody, do you understand?
Yeah.
And then from there, from there I am writing this equation. IA is VT minus EB over RA. Now everybody see, as I said, that EB is your back voltage. This is called the back voltage. So here is the thing. Now everybody look this equation. At the very beginning means you are applying the voltage, but still the shaft has not started rotating. Still the shaft is not rotating. If the shaft does not rotate, this means that your EB is 0. Do you understand this one? Because what I explained, that once the motor has started rotating, then this back voltage build up. This means that unless the shaft rotates, back voltage will be 0. So therefore, if the back voltage is 0, what you will notice? What will be the value of the current? Can you guess? Typically armature resistance is very, very small. like it is typically 1 ohm range or even less than 1 ohm, very small resistance. Because this is mainly coil inductance, it has very small resistance. So RA in real practice is very, very low, typically around 1 ohm. So therefore, now everybody see, look this equation. So therefore you can guess the value of the current. If you are applying 120 volt here to the DC motor, this means that you can guess 120 over that one, it is 120 ampere, which is very high. So in our laboratory, in our lab, we don't have such ammeter that have such higher rating. So it is very rare. So, and then what will happen, not only your equipment issue that you don't have the ammeter to measure, these coils will be burnt. These coils will be burnt. If you just apply the 120 volt and then motor is not running and the back voltage is 0. So according to this equation, because the high value of current will flow through the coils, these coils may be burnt up immediately. So that's why what you have to do, you have to insert a resistance. Now everybody see the equation. At the beginning of the operation, if you add some parameter, this is called the starter resistance, ST, RST, starter. This is the word, starter resistance. STARTER. This is called the starter resistance. Okay, so therefore, you have to add very high value of the starter resistance. If you add that starter resistance, then your current value will be small and that will protect the motor. So therefore, what happens here in series, you have to add that starter resistance, RST. Therefore, in fact, in the lab, when you will be doing the experiment, you don't need to do anything. These things internally designed, automatically at the beginning of the operation, this will be active in the circuit. This will automatically come in series with the array. So then it will protect your motor. And now see, once the back voltage had built up, you see that once the shaft has started rotating, this is rotating, and your EB has built up. Now see the equation. Now gradually, automatically, IA will be small because VT minus EB. Of course, I mean, the DC motor principle is that VT must be greater than EB. EB cannot be greater than, or EB even cannot be equal to the VT. Because if VT equal to EB, then your IA will be 0, meaning that no current is going. This is your IA. So again, the motor will be stopped. So it is not allowed that EB will be equal to VT. Therefore, always VT is greater than EB. So once the back voltage is built up, everybody see, this means that you have in the numerator, if value will be small, then you don't need RST. Then you cancel the RST, meaning that you sorted out that RST you added initially. Once the EB has built up, it has significant amount, then you sort it out. Therefore, this thing will happen internally. Just I am explaining you the phenomenon. Could you follow me, everybody?
Yeah.
Yes. So does this make sense? Yeah. So that's why I saved this one. I am now taking you to that slide and you can understand. Now everybody read this one. So this is my back voltage equation in DC motor. I wrote down from here like IA E minus VT over RA. Now everybody read the what is starter. To protect the armature from initial high current, a starter, which is called series resistance, is used in the DC motor. And once the back EMF is developed, the starter resistance is sorted out. So therefore, I will be asking you this question: why is starter used in case of a DC motor? Or what is the function of starter in DC motor? Then exactly you will be writing this thing. I mean, you might express different way, but this should be the meaning. That you should say that in case of DC motor, initially high current flows through the coil. So why high current flows? Because initially there is no back voltage. Initially the back voltage is 0. So only voltage, applied voltage is the VT. So consequently current value will be very high, and that might be damaging for the coils, even might be burnt out straightforward. That's why you have to connect a series resistance with the armature coil. But then once back voltage is built up, then you have to sort it out. So the question is, why you need to sort it out? You have to sort it out because if you always keep that one turn on in the system, the series resistance, then current value will be very, very small. So then motor might not be started. So that's why at the beginning you need to protect the armature from initial high current, but then later, once the back voltage has been built up, then you have to take it out. This means that it is sorted out. Therefore, this thing will happen internally. Just I am explaining you that what happens inside the DC motor. Okay, so here everybody say, I have written down one term that speed of a DC motor n equal to E over K phi. So I have derived this equation from this one. So everybody look this equation, voltage equation. So if you look this equation, what is the main variable? Main variable is the phi, amount of flux, and n is the speed. Your G, total number of conductors, it is fixed. It is constant for a generator. Once you set up a new generator, definitely you will be fixed this number. And then pole number, this is fixed. Number of parallel path, all these fixed. This is 60. So only variable is phi and n. So therefore you can say the remaining terms z over 60 multiplied by phi pi, that's just the constant. And that constant you can represent by the symbol k, which is this k. Now look everybody, this equation, E equal to k phi n. You see z over 60 phi by a, because those are constant, that is I am representing by k. So this means here E equal to k phi n. From there I am writing what is n, E over k phi. So therefore, because now I am discussing the DC motor, but the equation should be the same both for motor and generator. The back voltage has also the same expression. This expression was we discussed at the beginning today, DC generator voltage, but the same equation applies for the back voltage, exactly the same thing. So that's why from there I am deriving this equation. Now, what you can see from this equation, in the denominator there is flux. Now everybody see, if the flux is 0, so what will be the speed? What will be the speed value if the flux is 0?
0.
Is it 0 or because infinity, right? There it will be infinity. So what does that mean of the infinity? Infinity means the motor will start rotating very, very, very fast. And it might happen that it might be wiped out from its mounting place because the speed is infinity theoretically. So, I mean, it might be burned, deformed, or immediately might be stopped. So that's why that is not recommended at all. You have to make sure before starting the motor that whatever the situation is, at least phi should not be 0. And what is that phi? That is the field flux, magnetic field flux. Therefore, rather than the armature coil, the field flux is very important in case of motor. Therefore, everybody, please you keep in mind that you will remember this equation, that you make sure that phi is not 0. If phi is 0, if you understand, then immediately shut down the line. I mean, don't attempt to start the motor because it will start spinning at very fast speed, might be wiped out from that place. So therefore, you might be asked this question, like I think at the end of the semester, the lab TA will take some sort of final quiz. you might be asked this question, that why the field circuit should not be left open for a DC motor. So this means field circuit keeping open means no current is flowing and then there is no flux. That is the meaning. So then exactly you will be explaining this thing, that if the field circuit is open, no current flows and there is no magnetization, in other words, if the flux is zero, then speed will be very, very high or infinity. And that's why it is suggested not to open the field circuit, never ever. So everybody, do you understand?
What if
Yeah,
you're
sure do.
really fast motor?
Yeah. So what you said, Jared?
What if you want a really fast motor? Would you open it then?
Yes, definitely. Okay, everybody, would you please write down this equation, the middle equation? Please write down now this equation. The generated or back voltage in a DC motor is Vt minus IAR. And then you see the meaning of the symbols. You know, E is the back voltage, Vt is the applied terminal voltage, I is the armature current, and R is the armature resistance. Please you all note down, and then I will take you another numerical problem. So you may not need to write down the last equation. This is just I explained. Today in the numerical problem, you don't need to use this one, but you need to use the middle equation. And then you already have the first equation. Have you all written down?
Yes, sir.
Okay.
Yep, got it.
Okay, great. The middle equation. Okay. Now I am taking you to another problem. Oh, I discussed this one. Okay. Everybody please read this problem. This is problem number 3 for today. A 100 kilowatt, 1000 volt, 60 hertz, 2-pole, 3-phase synchronous generator provides power to a 2-pole DC motor through a 3-phase rectifier. If the armature resistance of the motor is 0.95 ohm, then calculate the armature current of the motor when the back EMF of the motor is 1300 watt. The back EMF is actually the back voltage. So you all know that voltage is called electromotive force. EMF stands for electromotive force, which is the back voltage. It is the same. Motor is 1300. Assume full conduction of the rectifier. So what is happening, you see, although we are talking about the motor, but I am giving the motor voltage. This means Vt is coming from the 3-phase rectifier. And that 3-phase rectifier is getting power from a 3-phase generator. That is the meaning of this. And this is the very first line, 100 kilowatt, 1000 volt, 60 hertz, 2-pole. These all are the ratings for the synchronous generator. And that is providing power to the 2-pole DC motor via a 3-phase rectifier. This means because we are discussing DC motor, you need DC voltage to be applied at its terminal. That's why there is 3-phase rectifier. This means 3-phase synchronous generator is giving you the AC voltage, which is in this case 1000 volt RMS, line to line voltage. And then rectifier is converting into DC. And that DC is going to the motor. And then you see armature resistance is given. Then the question is, calculate the armature current of the motor. What is the IA value? Provided that the back voltage is 1300 volt. And for the rectifier, assume full conduction, meaning that the firing angle should be 0. Now, let me take you to the board. I am drawing the picture and then I believe you are able to solve. And here I have written down the answer. Let me take you to the board. I am drawing that picture. Okay. Let me clean off all of those things. Okay. This will be the schematic. So everybody draw with me. For example, this is that three-phase synchronous generator. That is first providing power to a three-phase rectifier, and that rectifier actually, for example, this is your RA, and this is that, sorry, DC motor, plus minus, give the direction, this is the IA. Okay, so here it is that your DC voltage, and here is that terminal voltage, VT applied here. This is your RA. Okay, then let me level. This is actually your DC motor. I'm not showing any shaft or anything, you understand this thing. And then this one is three-phase rectifier. This one is three-phase rectifier, this component. And this is three-phase. Three-phase synchronous generator, this body. And here the line voltage was mentioned, which is 1000 volt. Of course, this is A phase, this is B phase, and this is C phase. So you see, for that problem, this will be the schematic. So everybody say, this is your actually DC motor, and then it has the armature resistance. Although I am showing it here, but you assume that this is the part of the motor, brief schematic, and then the armature current is going through the array to the coil. So this means here you are getting VT. This is the applied voltage to the motor at these two terminals. This means definitely this portion is your DC and this side is AC. So keep in mind, because this is three-phase rectifier, on the left side it is AC, on the right side it is DC here. And then that DC voltage is going to the DC motor. Now this is the three-phase synchronous generator. That is the main power source to the rectifier and hence the motor. So here line to line voltage is 1000 volt. So everybody draw this schematic, then I am taking you to that statement and then you will be able to solve. Everybody please draw this brief schematic. Now, okay, let me write down one more thing, and then probably in on class I showed you what is the relationship between AC side and DC side. So you have to use this thing. So you know that on the AC side, this is the voltage, but what should be the voltage here? So you write down this one, that VDC. Probably you remember that once I mentioned this one in induction motor chapter. 3 Vm over pi, and then cosine of alpha. Cosine of alpha. This alpha is called the firing angle. So this means this alpha is called firing angle. So the statement says it is 0 degree. So firing angle is 0 degree because it is called the full conduction. Now Vm is your peak voltage. Write down the meaning. Peak AC voltage. Peak AC voltage. This Vm. So and then line to line, peak AC line voltage. Peak AC line voltage. That is the meaning of this is the pi symbol. So 3 Vm by pi cosine of alpha. That is the VDC. So therefore everybody say, keep in mind, this 1000 volt, that is the RMS. This is the RMS. This is the effective or RMS value. This is not the peak value, but in this equation, this Vm is the peak AC line voltage. So everybody, were you able to draw this diagram?
Yes, I have it now.
Okay, okay. So everybody, did you draw? So then I am taking you to that problem statement.
Got it.
Okay, okay. So I mean, already I saved it. So of course you can see this on again in the video. So once you have this picture, then now you see that statement. Okay, now read the statement, everybody. 100 kilowatt, 1000 volt, 60 hertz, 2-pole, 3-phase synchronous generator. Meaning that 1000 volt that I showed just now on the board, this is the RMS line-to-line voltage. Keep in mind, by default, this is the line-to-line voltage, RMS, but not the peak. So that is providing power to a 2-pole DC motor through a 3-phase rectifier. Now you see, if the armature resistance of the motor is 0.95, then what should be the armature current of the motor when the back voltage is 1300 volt? And assume full conduction of the rectifier. That's why you see just now I put alpha value is 0. Now using that VDC equation and then other equation that you have written down, you see, using the middle, everybody see the middle equation. With the help of this middle equation and the VDC equation that I showed in the board, can you calculate this one? And then are you getting 15.13?
How did you know alpha is 0?
Alpha 0, yeah.
How do you know that?
Oh, so see the very last sentence of the assume full conduction of the rectifier. So
Okay.
when it says full conduction means there is no delay, there is no angle delay. Immediately from the 0 point, the voltage and current is working through the rectifier. That is the meaning full conduction. So the full conduction means 0 degree alpha. So if there is any firing angle, then it will be clearly mentioned. Assume firing angle is 5 degree, 10 degree, whatever. But full conduction means it is fully working. There is no delay. That is the meaning.
Okay, thank you.
Okay. So then everybody please try use your pen and paper. And then are you getting this value? Let me know.
Yes.
Okay, great. Everybody, please try.
I'm a little tripped up on what is VT. I know you went through it and showed us what VDC was, how it's 3 times VP cosine alpha over pi. But I might not be getting the peak voltage correctly. It's the RMS times √3, right?
No, RMS time √2.
Times √2. Oh, yeah, my bad.
Yeah. So 3 at the beginning of the equation, 3 Vp or Vm, but that Vm is √2 multiplied by 1000. So therefore Vt should be greater than 1300 volt. Therefore, those who have already done, who are done, so you see that Vt terminal voltage of the motor must be greater than this 1300. Otherwise, your armature current will be negative. Everybody, I have approximated the answer, so you should get around that number, or you might just say 53 ampere, or could be a little bit higher, but it should be around 53. I just approximated this number. This is a pretty standard problem for motor generator, DC motor, DC generator. You might get this type of problem in your FE exam. And this is pretty standard. Therefore, you will be keeping your all the notes with you, even though like after completing this semester, you will be keeping all the notes, class material. That will help you to do well in the FE exam. Again, you might get at least 7-8 questions from this course, energy conversion course, for the FE exam. Are you all trying? Are you all getting? Jared, did you get this number?
Oh, I did. Yes.
Oh, okay, great. Yeah. Okay. So everybody see? So I have this one. You see that picture that I showed you on the board few minutes back? So this is the picture. So you see, I have mentioned here that back volt is 1300 volt. And then this is my main equation. I is Vt minus Cv over Ra. And I got that Vt 1350.47, which is coming from that equation, VDC 3 Vm by pi cosine of alpha. This alpha is 0 degree that I explained you. So 1350.47. So then, and this Ra value was 0.95. Finally, I got 53.13. This is the answer. Hey, Tyler, did you get this result?
Yeah, once I corrected the square root of 2, that
okay.
fixed it.
Okay, got it. Oh, otherwise it would be very large number. Yeah.
Yeah, I would have had like some, like, I think it would have given me like 1600 for VT, and that wouldn't have been good.
Yeah, because it was like √3 you did. It should be √2. You see, I mean, this is again not that difficult, but I mean, once you can write down this equation correctly, then you will be looking which parameters are given, which is not given. So in this case, CB is given, the VT is missing. That is your start point. Then you will be going back. That's why I am drawing a schematic. It is, you know, for every problem, it is better to draw a basic schematic, even the simple schematic, for your own understanding. You draw, and then what is missing? VT missing. Where is my VT? This is my VT. And then you look, how is it coming? How I will get. That's why your schematic will help you. Okay, that before to get VT, I have a rectifier, and the rectifier is getting powered from the generator. That will give you the answer, or that will give you the step what to do. Therefore, definitely, this is a synchronous generator. So this is the input to the rectifier, and output of the rectifier is your actually VT. There is the answer. So in that way, then you can find out, oh, what is the relationship? How I can relate this person. So this is the relationship. And once you do that, and then if you can properly, correctly put the parameters, then you are fine. So therefore, this is the main equation that you need. But here that VT is missing. That's why we are using this one. Everybody, could you follow me? Did you all get this result?
Yes.
Okay. Yeah, so please once again, because this is in the slide, after the class, you will be looking and you will be understanding. And then again, you might expect the similar problem in the upcoming midterm exam too. I think you are scheduled October 22, your midterm exam too. But then now I have started looking your midterm exam on. Hopefully next class, by next class, I can share you the grade for your midterm exam one. And then you make practice for this for the midterm exam too. That will be held in October 22. 1 week before I will give you a reminder of the exam too. Okay, I think there is one more problem that is for today that you practice, and then you are done. So everybody please read this one. A 60 Hertz, 11 kV, line-to-line RMS. I am clearly mentioning it that line-to-line RMS. Electric grid supplies power to an industrial DC motor through a 6-pulse thyristor bridge rectifier under full conduction. Again, the similar structure. Now, in order to minimize harmonics and provide a stiff DC voltage, a capacitor of 2.5 megajoule capacity is connected at the terminal of the motor. Then calculate the required capacitor volume. So therefore, once again, everybody notice the problem. First portion, first sentence says, you have an electric grid with the specification that is providing power to an DC motor with the help of a 6-pulse thyristor bridge rectifier. And then under full conduction mean alpha 0. Now, you know, because rectifier will produce DC, that DC has always some sort of ripple. So to minimize those harmonics and provide a steep DC voltage means constant DC voltage, you need a capacitor with 2.5 megajoule capacity that is connected at the motor terminal. Then what should be the capacitor value that can provide 2.5 megajoule capacity? So therefore, you see, in this case also, everybody see, let me take you to the board. I will be using that same, sorry. Okay, this one. Exactly, you can use the same diagram. I'm just a little bit cleaning up. Just let me a little bit clean up. Here you have a capacitor. The same diagram you can use. Here you have a capacitor. This is the capacitor C. And this is again, this is your VT. So the structure is the same. And this is your that. this is your 6 pulse bridge rectifier. This is called 6 pulse bridge rectifier, this component that is producing DC where there is some ripple, that's why you are adding a capacitor. And then I think in this case, this is not the correct value, yes. This is that grid system that is providing power to the motor through the 6-phase rectifier. So again, you need this conversion, this relationship, of course. Now everybody say, once you connect a capacitor and here the voltage is DC, so what is the property of capacitor? Capacitor can store energy. Capacitor can store energy because this is DC. So what is the capacitor energy storage? Is you can designate by that symbol is energy storage capacity across that half C VC square. This is in joule. The unit is in joule. Everybody, can you remember this equation? E equal to half CV square for capacitor. This means that if you know what is the voltage across the capacitor, so what is the voltage across the capacitor? Which is the same voltage, this VT, or the DC voltage that is coming from the AC side. This side is AC, and this side is your DC, which is coming from the AC side. That voltage appears across here, that will be this voltage. And if you know the energy storage capacity, then you can calculate the C value. Everybody, could you follow me? So everybody, please write down this equation. Energy storage is a half CV square for capacitor. And you need again this equation, VDC 3 Vm by pi cosine of alpha. This is the relationship between AC and DC side. So you need this on, and this is the schematic for the problem. And this will be your energy storage equation, AC half CV square. Has everybody written down this one?
Yeah, sure have.
Yeah, please you note down this one. Okay, and then once you have done that one, so then I'm taking you to that problem. Now read it. That 60 Hz 11 kV electric grid supplies power to an industrial DC motor through a 6-pulse bridge rectifier under full conduction. In order to minimize harmonics and provide a steep DC voltage, a capacitor of 2.5 megajoule capacity is connected at the terminal of the motor. This means that 2.5 megajoule is your energy storage value, E value. So the question is calculate the required capacitor value, find out the C value. Can you do that? And then you should be getting this result, 22.64 millifarad. Please verify that one. And this is the last problem for today. So therefore, I think I have done this one here. Again, you see that brief schematic. This is that capacitor. First, I am using that equation. Everybody look, VDC 3 Vm by pi cosine of alpha. Vm was, I think it was 11 kV. You see, 11 kV. So 11, I'm converting into volt. And then that root 2 cosine 0 degree. So I got 14.86 kV. And then I am using that equation for capacitor. AC half CVC square, which is 2.5 megajoule. So then I am calculating the C by plugging in VDC value here, which is VC. So that C is 22.64 millifarad. Everybody, can you check this calculation by your calculator?
Yep, I got it.
Okay, great. Nathan, did you get this same number?
Yep, I sure did.
Okay, great, great. Okay, so I think we're almost done in terms of timing. So this is class 14, so you can see, of course, you can see the video, but in terms of slide also, those are available on eCourseware. Already I uploaded this on yesterday. So everybody, please, you look and then take your pen, paper, and calculator, you make practice. So with that, I'm stopping here. We'll continue this chapter. At least we need one more class. There are different types of DC motor and different types of DC generator. And then we'll be looking the speed control method for DC motor. Those are also very important. Then we'll be done for this chapter. Okay, so I'm stopped for sharing.